Hello students, welcome back to another lecture, which is lecture number 24 in our discussion on classical mechanics. And in the last 2-3 classes we have been discussing on the two-body problem and Kepler's problem. Especially we have seen what are the symmetries present in the system using the Lagrangian and Hamiltonian method. And we have recognized and come to a very important point that even though three-dimensional space is available for the planetary system or the two-body system, even though three dimensions are available, the system really takes only 2 dimensions. Okay, which means that the dynamics of the two-body problem takes place only within the 2 dimension. That means planar motion. Okay, that the additional degrees of freedom, namely the 3rd dimension, it is not making use of. That means the physical system is not making use of the additional degrees of freedom. It itself is restricted to move within a plane, and the consequence and why this has happened, of course, is exclusively due to the nature of the central potential. That means the central potential is not going to depend on the angles. It is going to depend purely on the distance, being the scalar. Okay, you have to consider it as a scalar only, and because of that reason, there was a symmetry present in the system, especially in the phi direction, and that is the reason why it has made a very important conclusion that the dynamics takes place only in the 2 dimensions. This is a very important point, and this is extremely important conclusion. And because of that reason, our equations are going to be written down in the 2 dimensions, and then we can proceed further towards the calculation of the equation of orbit. Okay, so without that information, proceeding further is difficult. That is why the important point about the 2-dimensionality of the dynamics is concluded in the last class. So now we are going to write down the equation in the 2 dimension. So that is the reason why we have this kind of an explanation. So let us now write down the Lagrangian which we obtained in the last class. So whatever expression that we have written down in the last class, so there we will start, okay, and then we will proceed further. So it is actually the Lagrangian, you already know, half m into r dot square plus r square theta dot square plus r square sine square theta into phi dot square, and then you have the potential V of r. Now this is the expression that we got in the last class, and then made a conclusion that it is a 2-dimensional problem. So we will write down that it's a 2-dimensional problem, which means that we are going to remove the last term. Okay, so based on the last class work, you remove the last term, 3rd term, I mean to say the 3rd term in the kinetic energy. If you simply remove it, we are left out with the 2-dimensional Lagrangian, which is what I am writing now, plus r square theta dot square and close the bracket minus V of r. So this is the very important conclusion, and based on this, now we can proceed further by taking the Legendre transformation. Okay, now that we have obtained the Lagrangian, we are now moving forward to the Hamiltonian formulation, and therefore we will we will perform the Legendre transformations, which you already know what to do. Okay, so let me write down that. So the first step would be to write down the defining equations. Okay, so let me therefore write down those defining equations, then only we can proceed further. So we have the 2 defining equations actually, and you should know why there are 2. One for each coordinate. It is a 2-dimensional problem. So first we will write down for the r coordinate, and then we will write down for the theta coordinate, that is the expression for dou theta dot. And once we have these 2, we have to evaluate the partial derivatives from the Lagrangian. Okay, now we are going to perform the derivative. So we get m times how much m times r dot equal to pr, and then you can then simplify. Similarly for the 2nd term you can do, but let us finish the inversion step. This is the inversion step, which is r dot equal to pr divided by m, and come to the 2nd part, and similarly you can write down that 1 by 2, and then you have m into r square, then 2 times theta dot will be equal to p theta, and once you have that, you can now simplify. Okay, simplify means the inversion step, I mean to say. So the inversion step we are going to do now, and this is the inversion step what I am writing now. And then once we have this, let us think about giving the equation number. Okay, So mr square. Okay, so that is the inversion step for the theta variable. And so we have some equations. Let us give some kind of number, and one, let us say this is the first equation is Lagrangian, the second one will be the second and third one. Okay, whatever you call that inversion step I am calling. Okay, that is the point to be noted. And so let us substitute these equations in the original Lagrangian so that we will be getting the Hamiltonian. So let me write down the steps here. There is nothing to do here, so only simplification. Then plus r, okay, r square p theta square. I think there is a square here, therefore I'll have to write down m square r to the power of 4. Okay, and close the bracket, and then minus v of r. Okay, that's all about it. Okay, now we will write down the equation or the definition for the Hamiltonian. Okay, you know the Hamiltonian equation, pq dot minus L. Okay, that's what I'm going to write. It is a summation of the PIQI dot and then minus the Lagrangian. So let us evaluate this. H equal to PR, then we have a QR dot, then plus P theta, Q theta dot, then you have a minus Lagrangian. And now we will use the above equations, namely equation number 2, 3, I think 4. Okay, 2, 3 and 4. So let us use these three equations and simplify. Okay, so let us simplify this. It's only an algebraic step, so let me finish writing this. So here I am just taking the half m inside. So I'll write down as half m into, then we have PR square by m square, then plus half into, I think one m is cancelling. Okay, I think one m is cancelling. Then left out is p theta square by mr square. Okay, and r square is also cancelling. So r square I'll have. So I'll write down mr square. Then you have minus of the v of r. There's nothing to change there. And then we can just add and subtract. I think the first term and third term are similar. Okay, first term and third term are similar, so I can perform the subtraction. So I'll be getting PR square. You see, PR square divided by 2m. Then I have plus P theta square divided by 2mr square. Because second term and fourth terms are identical, I mean similar, so I can subtract them. Then we get a plus. So minus of minus is there. So let me write down as plus. Then I have a v of r, and that's all. And that is supposed to be the Hamiltonian. So let me write down it as h here. Okay, because this is the Hamiltonian. And let us probably this is the required equation. So let me put a box. And I think we can give some equation number for this. So let me give this as some equation number 7. So ultimately what I am writing is, this is the ultimate Hamiltonian that we are interested in. Okay. Okay, once that clarity is there, okay, now we can proceed to obtaining the Hamilton's equation of motion HEOM. So you already know what are the HEOM. So first let me write down the standard equations, okay, which means that Q dots and P dots. Okay, Hamilton equation means, so first you have to write down Q dot, then we will be writing for PI dot. So let me write down like that. So QI dots will be given by, it is the partial derivative of the Hamiltonian with respect to the dou pi. And not only that, corresponding pi dots will have to write down. So let me write down that. And we will say that pi dot will be equal to minus of the dou h divided by dou qi. And now we will have to evaluate the partial derivatives from equation number 7. That's all we have to perform. So which means that we have to perform 4 number of equations. So that is a point to be noted. Okay, so how it is 4? Let me explain. Why it is 4 is Hamiltonian is now a function of r comma theta comma, I think what are the PR comma P theta. So let me write down r comma theta comma PR comma P theta. So there are 4 of them are there, and therefore we will have to write down the 4 Hamilton's equation of motion. So let me put some kind of a box, and then for each one box I will write down 2 equations. Okay, then it will be clear how two equations are coming. So this first box we will be having 2 equations, and let me go later for the second box. Okay, so we have the equations r comma theta variable. So let me write down for the r variable, theta variable, and our job is only to calculate the partial derivatives. That's all about it. For clarity, I am writing as 2 equations for each of the degrees of freedom. So let us evaluate the partial derivatives now. So which means the standard equation you first write down. You can now understand what is happening. The I, suffix I is removed with the r. That is the point to be noted. Okay, and then the rest of the thing is simple. Let us evaluate. You have to go back and see the Hamiltonian and then write down. Okay, I am not going back in the screen. So if you are able to, what I mean to say is, you should have the equations with you in your note. Okay, then only it will be easy for you to see the equation and then take the partial derivative. So our first variable is therefore r variable. So q is a generic term, so that's why I am erasing q. Okay, so q is not a good idea. Now in particular q becomes r variable, so therefore I will write down as r dot. Okay, so first variable is r dot, so I will write down like that. So r dot will be equal to, you'll be having dou h divided by dou pr. Okay, and that is how you understand. And then evaluating the partial derivative, that we will do later. So let us now come to the theta variable and write down theta dot equal to dou h divided by dou p theta. So this is clear. And now let us see where are the 2 more equations. So after finishing only we will come to evaluate. So where are the 2 more equations which are going to come is pi dot. So let me put a box there, and then show how 2 more equations are coming. Okay, so if I am going to divide it into 2 parts, then we can say that the first part will be for the r variable. Okay, I think the first part will be for r variable, and I will write down the corresponding equation in terms of PR and P theta. So we have PR dot, I think. Yeah, PR dot, because the third variable is PR dot. PR dot will be equal to, we will be getting minus of the dou h by dou r, and similarly you can write down for the theta variable P theta dot equal to minus dou h by dou theta. So now we got the 4 equations. So for purpose of identifying the 4 equations, it is better to give some equation number. So let me give the first of the equation as equation number 8. I think the last equation was 7, right? I think 8 we can give. So let us start with I think 8, 9, 10 and 11 would be appropriate. So let us finish that. So let it be 8. Okay, equation number 8. This is the first Hamilton equation. Equation 9 will be the second Hamilton equation. Equation 10 will be the third Hamilton equation. And at last we have 11 as the final one. So now the purpose of writing this is that you will recognize that 4 equations are there. That is very important. So that is why numbers are given for the purpose of clarity. Once this is clear to you, now we will go to the Hamilton and then take the derivatives. That's all it is. So let us keep your Lagrangian, Hamiltonian with you and then perform the derivatives. Then only you can simplify this. That's what I'm writing. We can simplify by taking the partial derivative. So let me also write down. Let us calculate. Okay. Let us calculate. Okay, not. Let us calculate, and that is better. all partial derivatives we'll calculate. Okay, that's what I'm trying to write down. We'll calculate all the partial derivatives using equation number 7. Okay, that is the thing. And then we will be getting the following equations. Okay, so first one will become like this. R dot will be equal to PR and then divided by m. So those derivatives you can verify, because I don't want to go up and down in the screen. And then second equation, theta dot will be given by p theta divided by m times r square. So that will be the next equation. The point to be noted is I'm not changing the equation number. Let it be 8, 9, 10 and 11, because it is only evaluation of the partial derivative. So I know 10th so let us take 10th equation. Then I'll be getting PR dot. Okay, PR dot, I think then that should be equal to minus of p theta square. So you have to write down p theta square, then divided by this is little you have to carefully see mr cube, and then minus you have to perform derivative, so I'll put v prime. This is actually dv by dr. I am writing it as v prime, and similarly the last equation is the easiest equation where you get 0. Okay, so ultimately now we have the proper Hamilton's equations of motion where everything derivatives are calculated, and equation number 11 is the starting point for us. The starting point for the discussion is equation number 11, because there is something constant. Okay, so let us first write down that, okay, that it is a constant. Okay, so which means constant of the motion is fine, you can write down. And ultimately the point to be noted here is that let us explicitly write down that the constant is given by some symbol c. So that let me put the equation p theta equal to c, and then say that is the next equation, which is equation number 12. The purpose is to emphasize the c being a constant. That's all about it. Okay, later we will see what is the physical dimension, but before understanding the physical dimension, mathematically it's a constant. So that point I would like to clarify, or I would like to emphasize. Okay, so once that is clear to you, then we can proceed further to the next equation, namely equation number 9. Okay, from the equation number 9, what is there, you rearrange. Okay, you take a cross multiplication. P theta will be given by mr square theta dot. Okay, mr square theta dot, and then you have that's all. And similarly you can go to the next equation and then write down mr square theta dot equal to what we can say, that is also same thing, right? So it's the same constant, you write. So mr square theta dot equal to same constant c. That is what I was thinking about. P theta equal to c means mr square into theta dot is also c. So that is the meaning that I would like to say. So ultimately you see how what are we doing? We have the 4 Hamilton's equations of motion. Out of the 4, you start with the easiest equation. Okay, that is how you start with. You start with 11, and then after saying that the p theta is constant, what are you going to do next? Then you have to substitute that somewhere, right? So where to substitute, that is what you are thinking. Then I thought that equation number 9 would be an appropriate place to substitute that constant c. That is why I have written like this, that we can make use of the equation number 12 and say that mr square theta dot is a constant. Now a constant is mathematics, but in physics I would like to know what are the physical dimensions of mr square into theta dot. Okay, so in order to understand a better idea about the physical dimension, we can now think about substituting kilogram, meter, etc. In place of the mr square theta dot. Okay, that if you can do that job, you will be able to understand better the mr square into theta dot. So let me go to the next part of the board. I think this board is full. Okay, so either I have to erase this or I have to go. Okay, let me go to the somewhere else in the board and then make a physical dimensional analysis of this equation number 13. So keep note of 13 now. We are moving away from this place. Okay, so if you are writing down in the note, there is you will feel it more comfortable. Now I'm planning to do the dimensional analysis for mr square into theta dot. That's all I'm going to do. It's quite simple. So let us write down that. Okay, I think these things are simple, kilogram and meter, and that theta will be radians per second, etc. And then the whole thing should be, why I am writing like this is, this should be the dimension for the constant. See, even though constant C, that constant will have this dimension. So that point should be emphasized here. That is what I'm doing. And once you have kilogram meter square per second inverse, you must be in a position to recognize that it is a angular momentum. Okay, so our conclusion is that the constant C will have this dimension. Okay, that is the understanding. Okay, the constant C will have this dimension. So now you ask the question, if C is going to represent the angular momentum, that's what I'm writing actually. So mr square theta dot equal C means I want to ask the question whether you like the symbol C or you want to change the symbol. It's a matter of symbol. So C is having the angular momentum dimension. So mathematically you can use C, D, etc. So physically L is good, right? So I'm asking that question and I'm writing that a symbol L would be preferred. It's only a matter of preference. So the symbol L is preferred in place of C, and therefore we can write down as mr square theta dot equal to L. Okay, so it is actually same equation, but I am writing it as equation number 14. Just to say that it appears more physical. L means angular momentum. That's all about it. So equation 13 and equation 14 are identically same, and where I have only made a clarity between the constant C and then renaming it to L. That's all about it. And then once this is clear, then we can go back to our Hamiltonian and then write down this particular new expression that you got. Okay. So you have to actually, okay, let me write down. I have to search where is the Hamiltonian, and then I'll come back. So the plan is that we have to now rewrite the Hamiltonian. But I think equation number 7 I remember, but let us search where it is in the board and then I'll come back here. Okay, it is something like equation number 7 you search. If it is correct, then here it is there, equation number 7. So what I'm trying to say is this this place you'll have to substitute the L here. Okay, so remember that term and then come back to the original position now, and then write down that it was a p theta square. Okay, let me write down that p theta square is L square divided by, then you have a 2mr square, and then you have a plus v of r, plus v of r. So what is the change are you able to see? P theta square is being removed and we are putting in L square. That is a point to be noted. That's all about it. That is a place where we have changed. And then what happens is that are you able to see the two terms which I am going to put a bracket here. And what is that you want to understand is that these two terms are the terms corresponding to the R dependence. So we will call this as the effective potential. Simply you rename, there is nothing special. You are going to combine the two terms and give a new name, and that new name is called the effective potential for the two body problem. Okay, the point to be noted is V of R is the original potential, isn't it? So why we are calling another name is already V of R is the original potential that is there. Original potential means gravitational potential, okay, or electrostatic potential, both of them. That is the original one. L square by mr square has come mathematically from Hamiltonian. So let us club them together. After clubbing them, we will say effective potential. That's what I'm trying to say. And once you say that this is the equation number, some number we can give, and then we can write down some conclusion. Okay, we cannot make a direct conclusion, but however we need some kind of plotting. So let me write down that. Okay, we will be able to understand this equation number 15 if we can make some plotting. Okay, so that is what I am trying to write down. So we have this expression, namely the kinetic energy is the first term, and the quantity inside the bracket is the effective potential. So ultimately what I am trying to say is Hamiltonian doesn't have three terms, but Hamiltonian is having two terms. That is what I'm trying to say. Okay, only one potential energy is there, not two. That is what I mean to say. So which means that instead of saying that three terms are there, now we are having two terms. That is what I am saying, that by explicitly writing we will understand better. So let us write down that explicitly, that only two terms are visible in our Hamiltonian. Okay, so the V effective will be written down. So let us write down the V effective. Okay, we can understand better if we can plot only the effective potential, where the V effective is given by. Okay, so let me write down the effective potential. V effective equal to, that must be equal to L square divided by 2mr square. Then we have a minus. Yeah, here you have to think and write down something like alpha by r. You can write, where you can understand what is alpha by r. Something like gravitational potential. Okay, that's what I was telling you. When you write gravitational potential, what the alpha should be. Okay, you remember G m1 m2 by r square. If you remember that, now we can write down what could be the alpha there. So alpha can be equal to something like G into mass 1 into mass 2. By r you should not write. Okay, that divided by r is already there. No, alpha by r is there. So only we have to write down G into m1 into m2. So that is a constant, no need to worry. But only thing you need to note is that it's a positive number, right? So let us write down that it's a positive number. Nothing is negative there. So, and this is of course this is true for the first part also. So let me write down that this is true for the first part, L square. So I'll write down L square is also greater than 0. So if this is the situation, now it's time to give, or we can plot this particular equation by, say, giving some number now. So some number will give, probably 16 is okay. And now we can now we are ready to plot this graph. Then we can understand what is happening. Okay, so the graph will, what is the graph we are going to plot? Let me explain that. The graph should contain two graphs, one corresponding to the L square by 2mr square, and the second one corresponding to the alpha by r. So that is what you mean to say. Graph means there are two terms are there, right? So you be clear. Then now I will show the graph. There are two terms are there, L square by 2mr square. The second term is alpha by r. Alpha by r is negative. So we have to draw two graphs. Then we have to add them. That is the equation. Okay, so that is exactly what I am trying to do. And then I am plotting in another software and then bring it here right now. But remember that we are going to plot the negative alpha by r in some kind of a green color graph, so that you can distinguish. And then the plus L square by 2mr square I am trying to plot in red color. I am now bringing it. Yeah, so you must be able to see the green color graph, and that is the negative part. It's not clear. Once again I will bring it. Yeah, I think now it's okay. Okay, now it's coming. So alpha, that is the green color one, represents the minus alpha by r, and then the red color one represents plus L square by 2mr square. And then if you add these two, I will be getting the yellow color graph, which I am getting. So the yellow color graph is the ultimate one, which means that effective potential. So you understand what is effective potential? Yellow color graph is effective potential. So if these things are clear to you, and then from the appearance we can make some conclusions. So that is what I am trying to write down, that you should have the appearance of the graph, and then from the appearance of the graph we can write down some conclusion. Okay, let me write down that conclusion now. So you should have the graphs with you, then the conclusion would be better visible. So we are talking about the stability of the orbit, possible orbit. So when you'll have a stable orbit and when you'll have the unstable orbit. So now it should be clear that I am bringing the graph together here in the same board. So the advantage is you can see everything in one place. Now you'll be able to see that the green color one represents the minus alpha by r, and you must be able to recognize this by looking at the negative values here. So these are all the negative values of the y-axis, and you have the positive values of the y-axis, and therefore the red color curve is representing plus L square by 2m r square. Okay, the graph itself is attached with a minus sign. That is why all of these things are negative side. You should remember alpha is positive number, r is also a positive number. So that should be important, and we are plotting minus alpha by r as the graph. So the green color graph will be reaching infinity. So it is going deeply down. Why it is going deeply down is when r becomes small. When r becomes small, 1 by r will go to infinity, right? So that is why it is deeply going down, approaching the infinity. That is why the green color is looking like that, and the red color one is also a similar behavior. You have an r square in the denominator, and therefore when the r is becoming small, then once again it will reach the positive infinity. And where is r? Where is the r going to 0? When r will become small, here it is there. See, r values are the horizontal numbers or the r values. So this is r equal to 1. So you are going to smaller than 1 here. So when it is going to smaller than 1, you can think about when r equal to 0.01, when r equal to 0.001, 1 divided by r square will approach a large number, and that is why the red color graph is also reaching positive infinity. So this is the behavior of the two separate terms. Now we have to add the red color graph and the green color graph. So this addition you'll have to perform. If you add them, you get the yellow color graph. So this is the exercise that if you do, you'll be able to get this graph. After finishing all these things, there is very interesting thing happening. What is the interesting thing is, in the negative side also it is going to reach infinity, and in the positive side also it is trying to reach the infinity. So there is a competition between which infinity is going to be a larger number. Okay, infinity itself is not a number. Infinity means a large number. So you have two large number. So there is a fight between two large numbers, and the question is who is going to win. So that is why you are going to get some kind of a dip like this. That is called a minimum, and then ultimately what happens is who is going to win the competition is that the positive fellow is going to win the competition. That is L square divided by 2m r square will win the race or will the competition when r is approaching 0. Why this fellow is winning is because r square term is there. Okay, so that strength, r square strength is strong, is very strong when compared to r to the power 1. Here you don't have r square. Here it is only 1 by r. So the pulling power or the capability to run away to infinity is only r to the power 1. This fellow is running like r to the power 2. So he will run faster. So that is why the yellow color graph ultimately goes to the positive infinity. Okay, so overall the appearance is fine. Mathematically all these things are fine. Now the question that you will be asking is, how do I know that E less than 0 corresponds to the stable orbit, and how do you know that E greater than 0 means unstable? This is the very interesting point, and for this you will have to carefully think what is actually happening. Then you will be able to understand whatever it is. So let me therefore explain by considering some particular points in the graph. If you specifically consider some points in the graph, then you will be able to appreciate the advantage. So let me therefore consider a specific case. Say let me draw a line like this. I'll draw a horizontal line like that. Okay, if I draw like this, this line will continue there. Okay, so that is the line that I have. Now this particular line is an example corresponding to some constant value. I will say that the constant energy, namely the total energy. I am talking about total energy. Okay, so please note that otherwise this will be a great confusion for you. This E which I am going to represent is the total energy of the system. And let us say that this is some number. In our case, in the graph, you see this is 1 actually. We are not interested in saying 1 actually. Rather than we are interested to say E is greater than 0. So that is the condition that is written here, right? This tick mark. So therefore, that is E less than 0. So come to the greater than 0. Yeah, this is the one. So the line that I have drawn is the one corresponding to E greater than 0. So the total energy is greater than 0. Okay, then what is potential energy? You have to ask the question, what is potential energy? So for that, what you have to do is, suppose if I am standing here, you have to be carefully think. No, here you have to think, you have to pay the attention, otherwise you can't understand. Okay, if you pay attention for 5 minutes, okay, you will be able to follow what I am saying. So if I am going to stand here for some value of r, this is r value is actually something like 0.6. So if I am going to stand here, then if you come down, what is the value of the potential energy, you'll have to see. So the potential energy is actually minus 2.2. So there is a minus 2.2 value of the potential energy is there. So you subtract that. So let me calculate that. Okay. So if I calculate, you can understand. So E equal to, that is total energy equal to kinetic energy plus potential energy. Plus the potential energy. But however, what is your potential energy? Your potential energy is minus 2.2. So therefore, this is actually, this number, potential energy alone, takes the value minus 2.2. And then E takes the value 1. So you can see that E takes the value 1. Is the point clear? E takes the value 1. So therefore, what will be the kinetic energy? So you'll have to calculate what is kinetic energy. That is very simple, right? You can take to the left side. So kinetic energy is equal to, if you take it to the left side, I'll be getting 1 minus 2.2. So 1 minus 2.2. How much is that? That gives you a positive number. So that means kinetic energy will be given by 3.2. Do you agree for this? This should be something like, yeah, 1, you simply add 1. I think 3.2 is okay. I think I am not making numerical mistakes. Okay, so that should be 3.2. So 3.2 minus 2.2 will give you 1, right? You agree for that. Since the kinetic energy is positive, our conclusion is that it will keep moving. It has the kinetic energy, means it will keep move. So that is fine. But is there any place where kinetic energy can come to 0? So you have to be careful there. If the kinetic energy is approaching 0, then we say that the mass or the particle or the earth or the whatever you call the planet will be in a position to slow down and then come to the rest. If the kinetic energy is positive and large, it will move very fast. If the kinetic energy is small, it will be moving slowly. So you can at least understand what is the meaning of zero kinetic energy, where typically it will come to a kind of a rest position, temporary rest. It need not be all the time at rest, but at least for some time it will be at rest. It is like when something is oscillating. See, if you consider harmonic oscillator potential itself, you can imagine if this goes like that and then returns back at this last position, I mean what you call the last boundary position, it will temporarily, the mass will come here. Okay, it will come here and then return back, isn't it? So for a small fraction of a time, this particular oscillating mass is temporarily at rest. That is what I mean to say, that the kinetic energy is going to be 0. Okay, kinetic energy 0 is possible in dynamics. It will be momentarily, it will be at rest and then it will return its path. That kind of scenario is possible. Now what I am trying to say is that when the E is greater than 0, what happens is there is no possibility for the kinetic energy to go to 0. No way it can go to 0. Okay, wherever it be, if the particle is here, so this is the place where I have given the example. You can consider any other point on the line and then check out. You will discover that 0 value for the kinetic energy is not at all possible. So what happens is it will keep moving and then it will move away. It can't come near to this. Of course, you can ask the question, will it come to the yellow line? It cannot come to the yellow line because you see that there is a barrier here. So going to the infinity means you have an infinite potential here, and therefore it cannot come here. So at the worst situation, it can come near to the yellow color line. Yellow color line means practically speaking r equal to 0.3, something like that it can come, and then it may revert back and go away from the system. So which means that our conclusion is that it can go far away and it can come up to the yellow color line. So you are asking the question whether there is any bounded condition is there, and then our conclusion is that there is no bounding. Bounding means limited to certain region of space. So here there is no limiting of the space. So we say that unlimited space is available for the I will write down that. Conclusion is that the particular mass or the particular what you call the planet has unlimited space. I mean, the availability of the space, so it is not at all bounded. It can move anywhere. The only thing is it can come up to this. That's the only limiting case it has. The reason is because of the positive kinetic energy, and for all the right side one, you can calculate at every instant of the R, it has a positive kinetic energy, so it can go all the way up to infinity. So this graph shows only 4.2. See, this is 4.2. That's all. So if the graph is extended to 400, 4,000, 4 million, there is no end. You can keep going, and everywhere the kinetic energy is very large, so it will keep moving. So our conclusion is, therefore, it doesn't have any kind of stable situation, or we say that the orbit is going to be some kind of unbounded orbit. Okay, so we say that unbounded orbit. Let me write down that word also. Technical term, better to write down. So unbounded orbit. So unbounded orbit is the one corresponding to the case E greater than 0. Okay, but we have not done mathematical calculation, but in case if you are going to do the two-dimensional geometry and then perform the solution of the Hamilton's equation of motion, we can in fact obtain the equation of hyperbola. That is how it comes. Okay, only from the graph you cannot say it is hyperbola. You have to perform the solution to the Hamilton's equation of motion, and then the equation will tell you that it is in fact the hyperbola equation, because we know how the hyperbola equation will look like. X square by a square minus y square by b square will be equal to 1. That kind of equation is there, means it's hyperbola. So it all comes from the solution to the Hamilton's equation of motion. But for now, without doing those calculations, we can tell that the orbit is going to be unbounded orbit. So directly you can say like this: one example of unbounded orbit is hyperbola. So that's fine. Now let us come to another situation where let us consider the case of, say, something like we can say this number 1.6. So if the total energy is going to be 1.6, then I will also once again draw the horizontal line. If you draw the horizontal line like this throughout you draw, so that, which means that throughout this horizontal line, the total energy of the system, I'll write down the total energy of the system, is equal to some number like minus 1.6. But as I already told you, we are not interested in specific value, but instead we are going to say that this particular total energy is less than 0. So E less than 0 is the interesting point that we will have to consider. Now here what happens is, now there are 2 points are there. This is one point that you'll have to give attention, and there is another point where you'll have to give the attention. So these are the places where, these two places are the place where the kinetic energy can go to 0. Okay, the kinetic energy can go to 0 because of this equation. Equation is same, right? The total energy E equal to, total energy is E. Total energy E equal to, that's what I'm writing. Oh, sorry, not a vector. Okay, I put a vector there. Okay, let me remove the vector. So total energy E equal to the kinetic energy plus the potential energy. Now kinetic energy is less than 0, some number. Okay, you fix it as minus 1.6, and then the potential energy is given by the yellow color graph. Now what happens is, the yellow color graph and the white color graph has the same value at those points where I have put the arrow. Now since it is going to have the same value as the energy itself, at those places, I mean to say that these places, the kinetic energy is going to be 0 here and here. These are the two places where kinetic energy is 0, which means that if at all the planet is moving, then the planet has to come to rest temporarily. At least it has to come to temporarily at rest, those 2 points. And then once the planet is in between, then it will gain the kinetic energy, so it will increase its speed. Which means what? So the meaning should be clear. The meaning is that this is the physical location. So this is the x-axis, is the r-axis. This x-axis is the physical location r, and therefore now you say that r equal to this number. You go vertically like this. If you go vertically, you have a number here, And similarly for this point, you go straight like this and then find out that point. So you can now see that the particular planet will be bouncing in between these two regions. That's all. How it is going to bounce, that we don't know. Okay, whether it is going to bounce like a harmonic oscillators, try to push and pull that style, or it is going to perform some kind of an elliptic orbit or a circular orbit, that information we will not be knowing from the graph alone. Okay, so that has to be done from the solution to the Hamilton's equation. But without doing those calculations, we are now in a position to clearly tell that the orbit is going to be stable. Stable means it doesn't run away to infinity. That's the meaning. The planet will not run away to infinity. And therefore it is limited. Limited means it is called bounded. So let me write down now this particular technical term. And therefore we say that this is the bounded orbit will be there. And the bounded orbit can be anything. It can be a straight line orbit, go straight and come back. That is also bounded. Or it can do a circular orbit. You can keep on circulating in the same circle. Possible. You can also do some kind of an elliptic orbit. Possible. It can be any other geometrical structure, not necessarily straight line, not necessarily circle, ellipse, etc. Even then, some kind of a bounded orbit is possible. Okay, geometrically it can go somewhere. See, it can go like this. Okay, it can come in like this. So this is an example of an orbit which is not a circle, which is not an ellipse, which is not a straight line. What I'm trying to say is everything is possible. Right now we do not know. So if you want to know what is the nature of the orbit in a quantitative manner, you'll have to solve the Hamilton's equation of motion, and the solution clearly tells that it happens to be ellipse. So ellipse is coming from there. You solve it. Ultimately, the equation looks like x square by a square plus y square by b square equal to 1. That kind of equation ultimately it comes. And from there, we make a conclusion that it is an elliptical orbit. So the qualitative features are very important. E less than 0 and E greater than 0. E equal to 0 is some kind of a special situation where this horizontal line, let me draw this horizontal line here, which is actually this kind of line is the one corresponding to the E equal to 0 case, and E equal to 0 case also happens to be, okay, it also happens to be the unbounded, because the red color line is above. You see the red color line is above the E equal to 0. So what happens is ultimately it goes to the unbounded situation, and therefore mathematical calculation tells you that it is a parabolic orbit. So the one corresponding to the E equal to 0 is a parabolic orbit. So I'll write in PAR, right? So it goes to the parabolic orbit, and for E much greater than 0, you will be getting an hyperbolic orbit. And for E less than 0, we will be having an elliptical orbit. Okay, in particular, yeah, there is one interesting thing I didn't tell. Yeah, there is one point here which is the minimum of the entire curve. So you have a global minimum for the V effective potential. You know what is V effective potential? Yellow color graph is the V effective potential, and for that special situation, I'll write down that for the special situation we call that it is a turning point. The orbit happens to be a circular orbit. So let me write down that. Only for this special scenario, mathematical calculation show that the orbit happens to be a circular one. And all other cases like E less than 0, elliptical one. So remember, circular, elliptical, and hyperbolic and parabolic, these terminologies or these names will come only if we perform the exact solution to the Hamilton's equation. Okay, only from this graph such kind of conclusion cannot be done. So now this is at least now almost we have discussed most of the situation of the Hamilton's equation. There are some other points that can be discussed which are quite easy to discuss. One is that how are you going to establish or how are you going to prove the Kepler's 3 laws? Proving means whatever is observed by Kepler, that is in fact observable in Hamiltonian mechanics. That's the meaning of proof. Okay, it is easy to prove the first, second, and third laws by the solution. Where from you prove means there is nothing like special proof. You only solve the Hamilton's equation of motion. The solution to the Hamilton equation of motion will give you the proof of these 3 statements. That's all about it. So that is the only thing that can be done, which you can do hopefully. Okay. So as I already told in the last class, I'm planning to go to the next topic, probably something like rigid body dynamics or Small oscillation is very important topic. Either that can be done, and the another one is the introduction to tensor and the Lorentz transformation. So these topics are quite important. So maybe we'll focus this in the next class.